Hello everyone, and welcome back. Today, we are going to derive the third kinematic equation so that we may have it for our physics arsenal. Afterward, I'm then going to show you when it is most useful to use. We're going to do a visual derivation for this equation, and we're going to use the three graphs in front of us to do so. All three of them are velocity versus time graphs, and all three of them have slightly different shapes. Now, we are going to use a property of velocity versus time graphs that I've mentioned before. And that property is the fact that the area under the curve will get you the displacement. And we're going to start with this one on the left. Looking at this, my initial velocity here is 5 meters a second. Their final velocity is the same, and the time period is 10 seconds. So to get displacement, I would literally have to do height times base. It's a rectangle. I'm going to continue that. I would need to do VI times time. And I don't need to worry about VF because it's the same as VI. I will keep going here. 5 meters per second times 10 seconds. Seconds cancel, and I will get 50 meters. And if you think about it, it makes sense. 5 meters per second for 10 seconds, you're going to go 50 meters. Okay, taking a look at this second graph, this object starts from rest and speeds up to 3 meters a second. So in this case, my VI is 0 and my VF is 3 meters a second. And this shape is a triangle. So to get displacement, I need to do the area of a triangle, which is 1/2 height times base. In this case, that would be 1/2 the height, which is my VF, and my VI is 0, so I don't have to worry about it, times my base, which is my time. Continue this. I get 3 meters per second times 10 seconds. Again, seconds cancel. 3 divided by 2 is 1.5 times 10 would be 15 meters. All right, so if the person started at 5 meters a second and stayed at 5 meters a second, they will go 50 meters. If someone started from rest and increased their velocity to 3 meters per second, they would end up going 15 meters. All right, now I made those two so we can take a closer look at this one. We're going to find the area under this shape. And the fact that the initial velocity is 5 and it increases by 3 meters a second is not an accident. VI is 5 meters a second. VF is 8 meters a second, and of course the time period again is 10 seconds. So I'm actually going to do this in two parts. Displacement. First, I'm going to take a look at this rectangle shape here. Well, that's height times base, and the height is initial velocity. So VI times time will get you this displacement if the assumption was that this object did not speed up. However, it did speed up, which means I also need this triangle portion here. So I'm going to add that triangle portion, which is 1/2 height times base. To get the height is not 8 meters a second. I only want the height of the triangle. So the height is the difference between the 5 meters a second and the 8, which would be 3. Or VF minus VI, the 8 minus the 5, multiplied by the base will get me the area in that triangle. Just to make sure we're on the right track, this one shape should combine to match these two. So VI times time, 5 meters a second, times 10 seconds, plus 1/2. VF minus VI is 3 meters per second, because 8 minus 5, times 10 seconds. These seconds cancel. These seconds cancel. I get 50 meters plus 15 meters, which is for a total of 65 meters. So this works out fine. So we're going to take a closer look at this combined relationship now. And the important thing I want to point out right now is that this equation works in two parts, where this first part is the constant velocity section. If your object did not change velocity, this gets you the displacement. However, This second section either adds onto or subtracts from that displacement. If this person was slowing down, so instead of this top area, I would have this rectangle, then I would have VF minus VI, and VF will be down here. Let's say VF was 2 meters a second. I would have 2 minus 5, which would get me a negative number, which would mean I would have the rectangle here, then this second part wouldn't add a triangle, it would subtract it. And I would have just this part here as my shape, as my displacement. So this first part gets you the rectangle. This second part either adds or subtracts the triangle. It adds or subtracts displacement whether or not the object is speeding up or slowing down. If the object is speeding up, it will add displacement to the first part. If it is slowing down, it will subtract displacement from the first part. Now that we have this down, let's take a look at that equation because we're going to play with it a little bit. I'm really only going to make one change here. And what I'm going to do is basically a little bit of reverse algebra. Normally in algebra, you would cancel things out, but I'm going to do the exact opposite with this last part here. I am going to both multiply and divide by time. So what happens if I do that? Well, one thing I want you to look at is what I'm circling right now. Do you recognize what that is? So again, this first part is the rectangle, the constant velocity portion. The second part deals with an increase or decrease in velocity, and another word for that, of course, is acceleration. The part I circled is change in velocity over time, and I no longer have time here, I have time squared. So this equation will get you the displacement if you know the initial velocity, the acceleration, and the time. And again, the second portion here will either add on to the displacement or subtract from it, depending on whether the acceleration is increasing the velocity or decreasing the velocity. Right now, this basically is a shortcut between the first two kinematic equations. Without this, the problems you deal with actually probably wouldn't be that different. You would just need to use the first two kinematic equations separately. But this one allows you to get the displacement in one shot with this information. However, this equation is extremely useful in two particular situations. So now that I have this on a new screen, I want to show you the two very specific and very easy to identify situations where this third kinematic equation becomes extremely useful. The first is if your acceleration is 0 meters a second squared. That means the object is moving at a constant velocity. If that happens, this equation boils down very simply to VI times time, because this entire second section cancels out. That means basically you have displacement is velocity times time because your velocity is constant. The second most useful situation is actually very similar. It is if velocity initial is 0 meters per second, because the first part of the equation cancels out, and you get displacement is 1/2 acceleration times time squared. Where this becomes really useful is if VI is 0 and you're asked how much time does it take for something to happen. If I rearrange this for time, I'll get 2 times displacement over acceleration square root. This will become extremely useful when we get into free fall, two-dimensional kinematics, and projectile motion. So if you recognize a situation where either the acceleration is 0 or initial velocity is 0, take a look at this third kinematic equation. Very commonly, you can get some good information from it very quickly. Now, I split the screen because there's something else I want to mention. This typically is not how you will see the equation on an actual physics equation sheet, like for the AP exam. So there's some things I want to clarify. The first is the fact that I have been using delta D for displacement. Typically, you will see delta X used as displacement because displacement is change in position. And the assumption is that x initial and x final are your positions on the x-axis. So displacement is change in position would be position final minus position initial. I would use p, except p is actually taken up by another variable in physics. Now, if I was to rewrite this equation, it would be delta x vi times time plus 1/2 a delta t squared, or position final minus position initial equals vi times time plus 1/2 a delta t squared. However, it is most commonly written like this. Position final equals position initial plus vi times time plus 1/2 a v squared, where this equation solves directly for final position if you're given the initial position. I usually don't like writing it this way because none of the other kinematic equations have position in them, unless you literally want to separate the displacement out. It is typically written as delta d or delta x, which means you're solving for displacement. Not to mention, if you know the initial position and you have the displacement, getting the final position is actually quite easy. All it would be is final position is initial position plus displacement. And the other reason I do not like using delta x is because I specifically use delta x for the x-axis. And these kinematic equations work on any linear axis, whether it's left, right, up, down, or slanted on a hill. This equation will work in any one dimension, as will the other three kinematic equations. So, quick recap. Here are the 4 equations we have so far. First up is the first kinematic equation, which was derived off constant velocity. Constant velocity is displacement divided by time, or 1/2 vi plus vf, as long as acceleration is constant. The second equation is the acceleration equation. Acceleration by definition is change of velocity over time, vf minus vi over delta t. And while I'm here, we've also gone over Newton's second law. Acceleration is net force over mass. We just derived the third kinematic equation, displacement equals vi times time, which is the constant velocity portion, plus 1/2 a delta t squared, which either adds on or subtracts displacement depending on whether the object is increasing velocity or decreasing velocity. So we have now 4 equations in our arsenal. Hopefully you can put them to some good use. That's it for today. This is Mr. M, signing off.